Thank you, Ben. So it's really a great pleasure to be here, and I think this interaction between random matrices and operator algebras is something that has had huge influence on the field and on me personally, and it's great to be able to talk to each other and have more of these interactions and to meet many people that I know from their papers in person. I was asked by the organizers to give a mini course on strong convergence. So this is an area that has had many exciting developments in recent years, both in the sense that we have now many new tools and techniques that make it possible to prove strong convergence in all kinds of situations that were out of reach before, and in that there have been like really spectacular applications of strong convergence to several different areas of mathematics, kind of quite unexpectedly in some cases. So it's kind of it's kind of an exciting time, and so when I was asked to give a mini course about it, I wasn't quite sure what I should do. One thing I could have done after Ben's mini course is just prove the random matrix result that he needs, and I could have done this probably in 2 hours. However, you're going to hear many talks about this during this workshop, right? So we heard yesterday a wonderful talk by Benoit Collins. On Friday morning, there's going to be a series of 3 talks giving 2 different proofs of the same thing. So rather than doing that, I thought I would do the complete opposite of what Ben did in his mini course, and I'd give you a kind of survey about strong convergence, how it's been used in different areas of mathematics. Where are these applications coming from, and say much less about methods of proof, which you will hear in other talks. Okay, so that is my plan. And if I have time at the very end of my second lecture, I will tell you some kind of general properties of strong convergence that are very useful in not for a specific method of proof, but for a lot of different methods of proof. So maybe we should start by defining strong convergence. So let's be clear. Of course, you saw it in several talks. So what we do is we take some sequence of random matrices, and we take some limiting object, x, which is going to be x1 to xr, in some C-star algebra, A, right? And we say that xn converges to x strongly if the norm of any star polynomial of this set of random matrices xn converges to the norm of the limiting object x in probability for all star polynomials. I'll use the notation that was used yesterday. So for all non-commutative polynomials of these objects and their adjuncts. Now, you immediately see that I have here a slightly different definition than was given by Ben. So if in this definition you replace the norm by the trace, the normalized trace, that's called weak convergence. Okay? And Ben defines strong convergence to be weak convergence plus this property. I'm not going to define it that way. But of course, in all interesting situations, weak convergence will hold before strong convergence. And if I have time at the end, I'll explain to you that actually, formally speaking, weak convergence is a consequence of strong convergence. Okay, so, but we will see that later. So this is a basic definition, and depending on what limiting object you take and what random matrices you take, you get strong convergence statements that you may or may not be able to. Okay? So the origin of this notion is in this famous paper by Hagerup and Thorbjørnsen. For all p in, thank you, for all polynomials. So the origin of this notion is in this beautiful paper of Hagerup and Thorbjørnsen, and they prove that if these are GUE random matrices, so these are complex Gaussian random matrices, the usual model of complex Gaussian random matrices, and this is something called a free semicircular family. I'm not going to define it. Then we have this strong convergence. And that was the first result. And from the very beginning of this theory, this notion was motivated by applications to operator algebras. And so, for example, in this paper of Hagler and Johansson, they proved using that result that the X invariant of the reduced C-star algebra of the free group is not a group. That had been an old open problem at the time. In a sense, what, to know that you can approximate the C-star algebra in norm, right? In norm by finite dimensional things, gives you very strong control that allows you to prove such statements. And since this paper, there have been several very important applications in operator algebras.
What's the X invariant?
What? I don't want to define it. I'm not sure that I could scrounge up a definition off the top of my head anyway. So I'll leave that to other people to do. The only thing you need to know is it was an old open problem and they solved it like that. Okay, so this is. Ben, what year is your paper?
20.
20? I'll take your word for it. So there's much coming in between here, but I think it's kind of a culmination of many of these ideas. Ben gave a proof of the Peterson-Thom conjecture. Of course, at the time when Ben wrote this paper, it wasn't yet a proof because that statement wasn't known. But later, nowadays, we have many proofs of this statement for the model that Ben needs that he discussed in his talk. And it solves another long-standing problem, this time in this theory of von Neumann algebras rather than the theory of C-star algebras. Okay, but I'm not going to talk very much about these things. Ben gave an entire mini course about this story over here. And so I'm just saying that this connection between kind of questions in operator algebras that seem to have nothing to do with random matrices, and random matrices has been enormously fruitful. Okay. So what I want to do now is I want to talk about an entirely different set of applications of this notion that have arisen in recent years. So in recent years, there have been several kind of surprising breakthroughs in other areas of mathematics that have come from that same notion. And I want to tell you a little bit about them, where they come from, and to give you some idea about why strong convergence is important and why does it help us solve difficult problems in other areas of mathematics, not operator algebras. And this story is about optimal spectral gaps. So let me start with the very kind of classical question along these lines that dates back to the 80s, which is in graph theory. So let Gn be a sequence of d-regular graphs with n vertices. I just take a sequence of d-regular graphs with n vertices. Now, right, so it just means it's a graph, and every point has d neighbors. And I'm going to call AN is the adjacency matrix of this graph. Right? So I just put a 1. Right? Every entry from I to j, I put a 1 if there's an edge from I to j. So what you immediately see that if I hit this matrix AN on the vector of all 1s, this is just a vector all of whose entries are 1, right? Every row of this matrix has exactly d 1s, right? So this is exactly d times the vector of all 1s. Which means by the Perron-Frobenius theorem that the largest eigenvalue of the adjacency matrix is always d, and it has this eigenvector of all 1s. Okay? So every d-regular graph has this property, that its largest eigenvalue is d. Okay? And then there's a basic question that arises, which is what can we say about the other eigenvalues? Okay? So what can we say about eigenvalues 2 through n? That's the question. Now, notice that this is nothing else than the norm of some matrix. What matrix is it? So this AN is a self-adjoint matrix. It has largest eigenvalue d, so I can just remove the largest eigenvector, right? So I can look in the orthogonal complement of the largest eigenvector, And the norm of that matrix is exactly the maximum of the remaining eigenvalues. Okay? So this is AN restricted to the orthogonal complement of the trivial eigenvector. So that's the question that we're asking. Is it clear? Okay. So why do you care about this? Well, there are many reasons to care about these kind of questions, but let me give you the kind of party line from probability theory, right? Let's say I have a graph, and I do a random walk on this graph, right? So I start at a point, I pick a neighbor uniformly at random, I go there. I pick a neighbor uniformly at random, I go there, right? So you kind of explore the graph randomly by wandering around this graph. And, after a long time, you will, even if I start at a given fixed point, after a long time, you will be kind of uniformly distributed over all the vertices. And you might want to know, how long does it take, right? How long does it take to explore the graph, right? And so it's a basic fact, it's just linear algebra, that the rate of convergence, right? So how fast this random walk converges to a uniform distribution over the vertices is controlled exactly by this quantity, right? So if you have a handle on this quantity, you know how quickly you can explore a graph. And now you might wonder, if I have a d-regular graph, is it possible to explore this graph arbitrarily quickly, right? Are there graphs for which I can go arbitrarily quickly to the invariant distribution? And the answer seems that it should be no, right? Because every vertex only has d neighbors, right? So how fast can you go already? You don't have many options. And that is true, but there's a very precise statement of this due to Alon and Bopana from the 80s, which states that this quantity we're interested in is always lower bounded by this number 2 square root d minus 1 minus something that goes to 0 as the number of vertices goes to infinity. So we fix the degree of the graph and we let the number of vertices go to infinity. There is always, no matter what graphs we take. So here I didn't take any special graphs. Any sequence of d-regular graphs if the number of vertices go to infinity, there's a universal lower bound on the non-trivial eigenvalue. And you should really think of this as a kind of speed limit for how fast you can explore these graphs. Right? If I have a d-regular graph, a large d-regular graph, you cannot arbitrarily fast explore this graph. There's a kind of speed limit which is given by this inequality. And as this number over here, this is not just a weird number. This is exactly the spectral radius of the infinite d-regular tree. That's this quantity. And actually, the proof of this result is very easy. Okay, so what do? You just look, we look at the moments of the matrix rather than the norm. So you look at the moments of an adjacency matrix, just count the number of closed walks of length k, if it's the kth moment. And then you realize that in any d-regular graph, the number of closed walks of length k is lower bounded by the number of closed walks of length k in the d-regular tree. Right? Because if you want to go out from a vertex in the tree and come back, you always have to backtrack, right? Because it's a tree. Whereas in the graph, you could backtrack, but you could also go along a non-trivial cycle, right? So there are just less walks. And if you massage this using the spectral theorem, you will exactly get this. So it shows that there is some kind of speed limit for any graphs, not nice graphs. For any graphs, there's a kind of speed limit that comes from this infinite object, the infinite irregularity. And once you have this lower bound, then of course the completely natural question that you ask is, well, are there nice graphs that achieve this lower bound, right? So can we construct a sequence of graphs Gn so that this is also an upper bound? Right? It's a completely natural question. And those are the graphs that you can explore the fastest, right? Those are the d-regular graphs you can explore the fastest. So now I don't know what, of course I'm describing here old stuff, right? But if you just think about this question without context, let's take for granted for a moment that the answer is yes, you can construct such graphs, okay? I'm not giving away anything deep, okay? So we can construct these graphs. But, what kind of graphs should you be looking for, right? So I think you could have kind of two intuitions, right? One intuition is that these are the best possible graphs. These are the most beautiful, amazing graphs that exist, right? That meet this bound. So they should be very special, right? These should be very special. You should have to work hard to make your graph the absolute best, right? That would be one kind of intuition you would have. And this intuition, you would get this even more if you look at the first constructions of such graphs that meet this bound. They were constructed by famous papers of Lubotsky, Philip Sarnak, and Margulis independently using extremely deep number theory. Okay, they use this solution to the Ramanujan conjectures. Yes?
Did we write minus little o of 1?
Minus little o of 1.
So could we interpret that as like a sequence of constants going to 0?
Yeah, so as the number, so for every sequence of graphs, one can make this explicit in terms of the number of vertices. It's like 1 over log n or something like that, but with some constant depending on d. But I just wrote it like this for simplicity. So there is some error here, which is going to 0 as the number of vertices goes to infinity. And I'm asking to reverse this bound so that I get an upper bound by 2 squared d minus 1 plus little o1. Okay. Actually, the number theoretic constructions give you an upper bound without the little o1. That's a separate story I don't want to go into for the purpose of this. Okay. But, you know, the original constructions were using number theory. They were using very deep number theory, right? The solution of the Ramanujan conjectures. I mean, this is like heavy stuff, right? So these were very beautiful, very special graphs. And then, but, you know, the other point of view you could have is that, you know, often, you know, the best kind of behavior, you can get it by looking at generic objects, right? So the other conjecture you could have, which is the complete opposite, is you wouldn't need special graphs. Actually, maybe if you pick random regular graphs, they would already attain this mount, right? Maybe this is actually very common behavior, right? Maybe many graphs have this property. And that turns out to be true. And that was a theorem of Friedman. Who says that random irregular graphs satisfy the upper bound. Less or equal 2 square root d minus 1 plus little o1 in probability. So actually, this speed limit, it turns out that if I just randomly pick a graph, I already meet the speed limit, right? Again, up to this error of little o1, which also appears in the lower. It's kind of amazing. Most graphs are the nicest possible graph. You have to work hard to find graphs that do not meet the speed limit. Actually, you don't have to work hard because any graph that you would naturally write down doesn't meet the speed limit, right? Like a grid or, you know, any kind of explicitly constructed graph, you know, usually doesn't meet the speed limit, but random graphs. So what does it have to do with strong convergence, right? This is a statement about graph theory. So I want to kind of deconstruct this statement and move towards a statement about strong convergence, which would be vastly more general than this. So I need to construct for you some random regular graphs. Actually, it's not quite clear what I mean by a random irregular graph. There are different definitions of random irregular graphs. I'm going to fix one. They turn out to be more or less equivalent in certain ways, but let me not get into that. And I'm going to work for simplicity. I'm going to work with D even. So I'm going to call D is 2 times R. You can also do these constructions for odd degree, but let's work with even degree for some. So what this statement is saying is that I have to construct a bunch of regular graphs that behave in the limit like the regular tree, right? So it would be useful to construct the regular graphs in the regular tree in a kind of parallel way. Okay, so let's try to construct the regular graphs in the regular tree in a parallel way. So for the regular tree, I'm going to construct it like this. I'm going to set the vertices to be the elements of the free group with R symbols. Okay, and I'm going to call this generators G1 through GR. So these are just words. These are just words in the letters G1 through GR and their inverses, right? Reduced words, right? So if I write G1 inverse, that disappears, but otherwise they're all words. So let's draw a picture of this, right? So what are the edges? Right? So each vertex, right? So each word in the free group, I connect, so its neighbors will be GI W and GI inverse W, for I is 1 to R. Right, so I have exactly, you see, 2R neighbors, which is D. 2R is D. Does that make sense? So if I draw a picture of this.
And the neighbors are not reduced words.
The neighbors.
That, you don't insist that GI be from a different.
So let's see. So you see.
Right, so
these are all reduced. They are reduced words, right?
Sorry, what I mean is that you don't insist that, for example, in the first one, that the left-hand element of the word is not GI.
No, no. Let's draw a picture. Let's draw a picture. So if I start the identity, what are the four neighbors? So let's do the picture in R equals 2, right, for simplicity. So the neighbors are what? G1, G1 inverse, G2, G2 inverse, right? So now what are the neighbors of G1? So I can have, there are four neighbors. One of them is if I multiply from left by G1 inverse, but then I go back to the identity. That's maybe answering your question. Then I can multiply here by G2 inverse. And here I go to G2, G1, and here I'll go to G1 squared. And similarly over here, right? I can go, so I can do G2 inverse, I go back to the identity, or I do G1, G2, right? G2 squared, G2, G1, what do I need here? G2? G1 inverse G2, thanks. That's it, right? So I can construct this way, I do this everywhere, I construct an infinite tree. Yes?
Just want to comment that this picture is handily in the icon for the workshop.
Yes.
So
that's why I took it. I mean, what I'm doing here will be obvious to anybody who's ever worked with a free group. But, you know, I just want to make explicit, these are not some kind of, you know, abstract representation, theoretic objects. I mean, these are tangible things that we can write down, right? So, in particular, let's write down what is the adjacency matrix of this tree, right? So this is an infinite matrix, right? Because the vertices is an infinite, countably infinite set, so it's an infinite matrix. And what do I do, right? So for every vertex, I just add up the matrices corresponding to each of these transformations, right? So there's a matrix that has an entry 1 in the entry that goes from W to WGI, right? That's nothing else than the left regular representation of the free group, okay? So the adjacency matrix of this infinite tree, A, is just a left regular representation of G1 plus the left regular representation of G1 inverse, which happens to be the adjoint, plus the left regular representation of GR, plus the left regular representation of GR. And you can think of each of these terms, for example, lambda G1 is just the adjacency matrix of the directed graph, which only has an edge from each word W to G1W. Right? So that's just the definition of the left regular representation. Are we good? Now, if I want to make a graph on, let's say, n vertices, I basically want to do the same thing, but I have to make it close, right? So that it has works in a finite number of vertices. So I'm going to do that rather than using these free generators, I'm going to draw a bunch of permutations. Okay? So the vertices is the set 1 through n. And how do I construct edges? So what am I going to do is I'm going to fix R permutations in the symmetric group on n elements, right? So I'm going to fix R permutations of n elements, right? So for each vertex, its neighbors will be what? Well, they will just be sigma I of V and sigma I inverse of V, where I is 1 to R, right? So the permutations tell me, right, which vertex I hook it up to the two elements that are connected to that vertex by the permutation, right? The one that the permutation sends it to and the one that is sent to it by the permutation. And you see these sigma I's and these GI's play exactly a parallel role in this construction. Right? So this is a completely parallel construction. So for example, I can draw such an object, right? So if I pick sigma 1, so here R again is 2. So if I pick the first permutation to be the cycle 1, 2, 3, right? Here is 1, 2, and 3, right? So it sends 1 to 2, and it says 3 to 1, right? So sigma 1 inverse of 1 is 3, so I connect these two guys, and it sends 2 to 3, right? So then I get a 2 regular graph. And now if I want to make a 4 regular graph, I have to add another permutation, so maybe I'll add this one over here, right? So this guy sends 1 to 1, and 2 to 3, and 3 to 2, right? So I get this graph, which is a 4 regular graph. And locally, this graph looks exactly like this graph, right? Because each of the edges, here, each of the edges is indexed by which generator I act on it, and here each of the edges emanating, right? Each of the 4 edges emanating from a vertex is indexed by which permutation I act on. Right? So it's a kind of parallel construction between these two objects.
Maybe you forgot 3 to 2 because for the question is only 3 regular, no?
I beg your pardon?
The degree should be twice, no? 2 to 3.
1, 2, 3. Ah, sorry, I have 2.
Yes.
I have 2 of them. Thank you. So you see, this construction doesn't necessarily give you a simple graph. It can have self-loops. It can have double edges, right? That's okay. If you really want a simple graph, it turns out that these graphs are simple with constant probability. So you can just condition on it. But that's a little detail I don't want to get into. So here, what is the adjacency matrix? Well, again, I can take the matrices which exactly have an element 1 from V to sigma I of V. That is known as a permutation matrix, right? So the adjacency matrix here is just the sum, so sigma Si is just a permutation matrix associated to sigma I. So it's just a sum of a bunch of permutation matrices. Here it was a sum of these regular representations of the free. Okay? Now this is a graph. For any set of permutations, I get a deregular graph. If I pick these permutations uniformly at random, I get a random deregular graph. So this is how we construct a random deregular graph. But you see, by construction, it's been designed to be a parallel to this infinite picture over here that we believe to be the limit. Okay? So if we have this language now, then we can reformulate Friedman's theorem. This is not a different theorem of Friedman. That's the same theorem. I'm just rewriting it in this notation. It says that if I take a bunch of IID random permutation matrices, and I have to remove the trivial eigenvalue, right, that the norm converges to exactly the same object where each of these guys is replaced by the same object that lives in the free group. Does it make sense? That's a statement. That's what Friedman's theorem says, just in this, this more sensible way. Are there any questions? Okay. So now this looks kind of lovely, right? Because we have a bunch of random matrices, and we have a bunch of infinite dimensional operators, and we're saying that somehow these random matrices behave like these infinite dimensional operators in the limit. It kind of smells like strong convergence. Except here we took a very special polynomial, which is just a polynomial, which is just x1 plus x1 adjoint. Right? So if I take this polynomial of these random matrices, then the norm converges in the limit to the same polynomial of these objects. Right? So this is like strong convergence, but only for one polynomial. Right? Now, that's certainly not the way Friedman thought about this problem, okay? But if we think about it this way, we can now make a huge leap of faith and say maybe this convergence is true not for one polynomial, but for every polynomial, right? That seems kind of like a ridiculous notion, but it's true, okay? And this was a very beautiful and very influential result of Bordunov and Collins. So it says that, in fact, not just this statement for this very special polynomial actually extends to any polynomial. Every star polynomial has the same property. So let me write it in 2 ways. One way to say it is if I take these random matrices, so these are just IID random n by n permutation matrices, but I have to remove the trivial eigenvalue. I just mean each of these matrices, they just act on this space, on the orthogonal space to the ones vector. Converges strongly to these limiting objects. And just, I mean, I deleted the definition of strong convergence. But simply what this means is that for all non-commutative star polynomials in R variables, the norm of this random matrix, which is just a polynomial of IID random permutation matrix, restricted to the non-trivial subspace, converges in probability to the same polynomial of the obvious limiting objects. So, yes.
One quick clarification.
Yes.
In probability, do you mean taking the expectation at each stage and then taking the limit, or no?
No, it means convergence in probability is that the probability that this differs from that by epsilon goes to 0 for every positive epsilon. And that's the definition of convergence in probability. So there is a subtle difference between convergence in probability and convergence of probability 1. This is, and it's kind of important in these models, unlike the models that, like GUE matrices that were studied before, these models don't have good concentration of measure properties. So we do have to make the distinction. But you see, this is a vast generalization of Friedman's theorem, right? I mean, it's hugely more general, right? Because if you restrict this to that particular polynomial, you get Friedman's theorem back. But this is true for every polynomial. Now the question is, why should you care, right? So, I mean, why is this such a useful result, right? Because right now it just looks like I kind of arbitrarily generalized, right, Friedman's theorem. But I mean, it's a kind of very vague statement. So why is strong convergence important? And I think, you know, I'm going to write down a kind of tautological statement, but roughly speaking, it's because polynomials, non-commutative polynomials, are extremely expressive. Right, so what this means is that we can encode many other problems in terms of some polynomials. Now, one example that you saw of this, I mean, in operator algebras, this is kind of obvious, okay? I mean, the fact that this is useful in kind of other, much more concrete problems is maybe less obvious. But, you know, one example I can give is if you go back to Ben's talk, right? What Ben was saying is I have a von Neumann algebra, right? Generated by the free group, and now I take a sub-algebra, right? And then somehow he wanted to encode the generators of that sub-algebra somehow in terms of polynomials of the generators of the big algebra. And the fact is that you have enough polynomials that you can make this encoding. And of course, how you do the encoding is highly non-trivial, and that's a lot of what Ben's lectures were about. Is that a fair? Yes, more or less. So, well, I mean, Ben's lecture had a whole bunch of other things that you need to do, but that's one of the, if you want to use strong convergence, you need to encode the object you're rolling. So I want to give you two kind of remarkable examples of problems where this is true, okay? And these problems are not like in operator algebras in the sense that one cares about specific models and one needs to somehow find a way to encode those specific models in terms of polynomials. So both of these questions are going to be some kind of generalization of the phenomenon that we see in Friedman's theorem in different directions. Okay? So if you want, right, what is Friedman's theorem saying? So Friedman's theorem is about d-regular graph, right? So there's the pair, there's Friedman and Alombo-Panna. So Alombo-Panna says that for every sequence of d-regular graphs, there is a kind of lower bound on the non-trivial eigenvalues that comes from the d-regular tree. And then Friedman's theorem says that there is a random construction of those d-regular graphs that really meets that bound. Right? So this idea shows up in many other places. For example, if we move away from d-regular graphs and we talk about arbitrary graphs, is there a similar thing? And it turns out there is a similar lower bound and there is a similar random construction. And we will see if we move away from graphs entirely and we look at other geometric objects, they're very similar phenomena. Okay? So I will give two kind of recent examples of this optimal spectral gap phenomenon. So the first one was already in this paper of Bordenov and Collins. So suppose that we want to prove something like Friedman's theorem, but not for regular graphs, but for graphs that may not necessarily be regular. Okay. So what is the right lower bound statement? Right? If the graph is not regular, then the deregular tree is not a natural notion. But there is a analog of Alombopana. Right? So what is so special about the deregular tree? It's that locally, every graph looks like, every deregular graph looks like the deregular tree. Right? In every neighborhood looks like a deregular tree. There's a completely general notion of this. I give you an arbitrary graph. There is always a tree that looks locally like the graph, which is the universal covering graph, the universal covering tree of the given graph. Okay? And just by repeating now, if you want to repeat now the proof of the Alombopana theorem, you get the following statement due to Greenberg. But it's really, I mean, more or less literally repeating the proof of Alombopana, which is that if Gn is a sequence of graphs with the number of vertices going to infinity, with the same universal cover, let's call it G tilde, then now I have to be very careful. Because it turns out that, well, let me write it this way. For this result, I don't need to be careful. The gap is always lower bounded by the spectral radius of the universal cover minus little o1. So the spectral radius of the universal cover replaces 2 square root d minus 1. If the universal cover was the deregular tree, this would exactly be 2 square root d minus 1. So now that we have a lower bound, we can ask, okay, are there random constructions that match this lower bound? So what we have to do is, starting from a given graph, or maybe starting from the tree or starting from a given graph, we have to find a way of constructing a sequence of larger and larger graphs that have the same universal cover. And there is a very natural construction called random lifts. So we start with any graph G, just a fixed graph on a finite number of vertices. Start with any graph G. It has a universal cover G tilde, right? And now I want to kind of amplify this graph. I want to make the graph larger and larger while keeping the same universal cover, okay? And I'll do it in a random way. So I'll create basically, rather than creating the universal cover, which is a cover, infinite fold cover, I will create finite covers of this graph. So how do you do this? You start by replicating this graph many times, right? So let's say my original graph was this triangle. So I create, let's say, I want to create the threefold cover, right? So I could create 3 copies of it. And 3, 3, 3, right? So I created 3 copies of this graph. Right, so every vertex has 3 duplicates now in the 3 graphs. And now what I can do, for example, the edge from 1 to 2, what I can do is I can create a cover by basically scrambling which duplicate of the graph each edge goes to. Right? Probably. Yes, thank you. So for example, if I take this edge 1 to 2, if I want to create a cover of the graph, what I can do is I can just kind of, rather than having it go to this 2, I could have it go to this 2, right? And then I could take this edge, right, for example, and I could send this guy to this 2, and I could take this edge and I could send it back to this guy, right? So this is a cover of the original triangle, right? I just scrambled, right? I took every existing edge and I scrambled where it goes to among the duplicates of the graph. And I can do this with every edge. For example, I can take this edge 1 to 3, and I can scramble it. I can let this one go to this 3 and this one go to this 1. And keep this one the same, right, etc., right? So we can keep doing this. Does it make sense? So given any graph, I can duplicate it, let's say, k times, and then for each edge, I just scramble which duplicate of the graph the endpoint goes to. And if I do this randomly, I get a random cover of the graph. Now, we have a little problem here, but it may not be obvious the way I constructed it. But any eigenvalue of the adjacency matrix of the original graph by construction will also be an eigenvalue of every one of these covers. So I can't necessarily prove this the way I wrote it, because I can't make eigenvalues of the original graph disappear. If the original graph had an eigenvalue that was smaller than the universal cover, right? Then I can't make it disappear by this construction. But what I can do is I can say that all of the new eigenvalues that I get by blowing up this graph are upper bounded by the universal cover. That's the best kind of result you can hope for. Right? So the theorem, which is due to Borden van Handel, is that all the new eigenvalues of Gn now doesn't have n vertices, but it's the n-fold cover of the original graph, right? So the number of vertices is n times the number of vertices of the original graph, are upper bounded by the spectral radius of the universal cover plus O1 in probability. That's the best result you can hope. Right? So in particular, if you start with an original graph such that all of its eigenvalues are bounded by the spectral radius of the universal cover, then it will be true asymptotically for all the lists. Yes?
Is the deregular case just a special case of this, where you have one vertex or something?
Yes, so the deregular case is a special case where the original graph G is one vertex, and I take R loops, R self loops. It's called a bouquet of loops. If I take this bouquet of loops and I apply it, I get exactly the original one. But this is a much more general one. Now, okay, again, I drew some pictures of graphs, right? But what is the secret here? So you can do this as an exercise for yourself. Just double check. What is the adjacency matrix? So the secret, a very simple formula, right? So the adjacency matrix of this n lift of the original graph can be expressed as a linear combination. So what do I do? For every edge, this is a sum over the edges in the graph, in G. These are edges of G. And for every edge, I have a random IID random permutation that I use to scramble them. Right? And then I can tensor on some matrix coefficients. And these matrix coefficients are extremely simple. So if the edge is ij, let's say I've just chosen it so I is less than j, then I can just choose AE to be the matrix which has a 1 in the ij entry and 0 elements. Okay. So I can just represent this adjacency matrix of this graph not as just a sum of random. I'd have to add the Hermitian conjugate to make it Hermitian. So I can represent this as a sum of random permutations of matrix coefficients. And now strong convergence. Okay, strong convergence says something about non-commutative polynomials. If I have time at the end of the second lecture, I will show you that strong convergence of non-commutative polynomials with scalar coefficients implies strong convergence of non-commutative polynomials with matrix coefficients. So even though this is a linear function that has matrix coefficients, this reduces to the strong convergence of polynomials with scalar coefficients, if you want. And therefore, the result of Borden van Handel says that the norm of this matrix on the orthogonal complement of the invariant subspace converges to the same object where I have the sum of AE tensor these lambda of GEs. Right? And that's exactly the adjacency matrix of the universal cover. So we see we've just taken whatever this construction is and encoded it in some special polynomials that capture the geometry of this space. So this was a very old problem, or very old. It was a problem of Noga alone and of Friedman to prove such a theorem, and it just follows as one very special instance of this strong convergence phenomenon. Yes? Hermitian conjugate. I mean, it needs to be a symmetric matrix, so I just wrote one half of it. Is there any question? Now, I want to tell you another more recent and I think very surprising application of the same nature, right? So the story here is the same, right? This phenomenon says we have some geometric object, we have some universal bound on its spectrum in terms of some covering object, and we want to understand whether there are constructions that meet that bound. Right? So far I've only talked about graphs. Now I'm going to talk about kind of remarkable result of Maggie and Hyde, which does something similar, I think 23. Does something very similar, but for, yes?
Sorry, could I actually ask a question about
Yes.
the general construction? So we said, like, was there starting, for our starting graph G in our example, was the idea for it to be just the triangle? Or like the
Well, in this picture that I drew, it was the triangle, but you can start with any graph you want.
Right,
So the
so-
triangle happens to be regular.
So are you specifically choosing the number 3 of copies of triangles, or are we imagining that we just keep having more and more copies of triangles?
Right, so Gn, and I took n triangles,
Sure.
or in general, n copies of any graph G. And then each edge, I scramble it randomly.
And we're considering that a universal cover, or,
The universal cover of this object is some tree.
right?
So in this case,
It would be like
these
a
are
straight
regular
line.
graphs. Right, I started with regular graphs, so in fact, I just get the regular tree. But in general, if I started with a graph that's not regular, then the universal cover would not be the regular tree. So the construction here, okay, you have to check what is the definition of the universal cover, okay? I didn't actually write it, but this construction preserves the universal cover of the graph. So if I start with a given graph that has this universal cover, then this construction preserves the universal cover of the graph. That's the point. But you should check that with the definition. I mean, it's hard for me to explain it without writing down the definition, and then, you know.
Yes, I think I'm aware of the definition.
Okay,
I wasn't
good.
sure if there's a different one.
No, there's no secret here, yes. Yeah.
What is Gn exactly in the construction?
So Gn is I took the original graph G, I duplicated it n times, so here n equals 3. I duplicated it n times, and then for each edge of the original graph, I chose the endpoint, I scrambled the endpoint using a uniform random permutation. Does that make sense? So these permutations are exactly these permutation matrices over here, right? Because I have the same number of permutations as I have edges in the original graph G.
So G tilde,
G tilde is the universal cover of the original graph G. This is a non-random object. It's a deterministic tree. Okay. So every vertex of this object is a non-back. It corresponds to a finite non-backtracking walk in the original graph. So this forms a tree. Yes.
Is there a way to reformulate things in terms of picking random subgroups of pi 1? Is that
Yes. This is very. Okay. Yeah, absolutely. And this is very important for the thing I'm going to write down next, even though I'm not going to actually write it that way. But absolutely, that's not random subgroups exactly. No, not random subgroups exactly. You want to take a quotient, but okay. We can discuss this later. So what Maggie and I did is kind of analogous picture to what happens in graphs, but for hyperbolic surfaces. So let's X be a hyperbolic surface. And a hyperbolic surface, this is just a quotient of the hyperbolic plane. So the universal cover is the hyperbolic plane. So this is this is not a graph, this is a continuous object. This is a two-dimensional surface. So you have a hyperbolic surface, its universal cover is always the hyperbolic plane. This plays the same role as d-regular graphs and d-regular tree. Okay. And now, what is the analog of Alombopana? Which is actually due to Huber, long before Alombopana. Okay, so this is from the 70s, this is from the 80s. The analog in this statement from of Alombopana, so we take the Laplacian on the surface, just a continuous Laplacian on this hyperbolic surface. So it has a trivial eigenvalue at 0. Right? So that corresponds to this one vector for graphs. Right? And the first non-trivial eigenvalue, so the first positive eigenvalue of the surface is always upper bounded by the bottom of the spectrum of the Laplacian on the universal cover. You have to be careful because for graphs and surfaces, the direction, right? Laplacians and adjacency matrices have the opposite convention, right? For Laplacians, the eigenvalues go up. For adjacency matrices, the eigenvalues go down. So that's why the inequality has been reversed. But it's the same statement as Alombopana. Let me make it compact. I mean, there's some statement for non-compact, but let me make it compact. And this number is 1/4. You can compute it. So the square root, 2 square root d minus 1 is 1/4 in this context. And what am I saying here? But this is 1/4. But of course, there's a plus little o1. And now what plays the role of the number of vertices? It's the genus. I take a sequence of compact hyperbolic surfaces with genus going to infinity, and asymptotically, the first non-trivial eigenvalue of the Laplace is always upper bounded by the bottom of the spectrum of the hyperbolic plane, which is the universal cover. And this is the exact analog of what we see here and what we see in the normal plan.
Is this quarter related to the sort of number of generators of SL2Z?
The number of generators of...
Well, I mean...
The 1/4?
Yeah.
I mean,
is there a D that goes with it?
this is I'm not sure, but maybe the answer is yes, but I would say that this object is an object whose spectrum you can compute explicitly, and it's 1/4. So, yeah, it's just a calculation. Yeah. So now that we have this upper bound, right, now of course we have the same question, right, which is we know that there is a kind of speed limit if we run a Brownian motion on a hyperbolic surface. There's a kind of speed limit for how fast it can mix, right, so for how fast it can cover the surface. And now the question is, can we find hyperbolic surfaces with genus going for infinity that match this bound? Right? That's the same question as for graphs, but now in the context of surfaces. Right? And you forget about random, right? It was actually a question whether there exists any sequence of hyperbolic surfaces with genus going to infinity that has this property, right? Now, in the case of graphs, we have these beautiful number theoretic constructions of graphs. They came first, and the random result came later. But in this story, actually, there was no construction known before the paper of Maggie and Hyde that attains this bound. So the natural question, which was a conjecture of Boozer, which is, do there exist some sequence of these hyperbolic surfaces with genus G, right, such that the, let's say, the lambda 1 of the Laplacian of xn, of xg, converges to 1/4 as g goes to infinity. This is a conjecture from the 80s. Yes?
Can I ask, so when you have a graph, in the graph case, you label a graph with edges and vertices, and here you have a surface, and it's it'll, like in this case, it's hyperbolic. We have a geometry on the surface, but we'll no longer have a notion of, I guess, like vertices or something, or edges. So I'm wondering, like, I guess we don't need that in terms of when we generalize in the graph case. Would, like, our choices of edges and vertices on the space give a geometric structure to work with? That would be an analog to, like, the geometry of the...
So, I can draw a picture for you, but I'm not sure it's entirely correct. Let me draw a picture. So, here's a hyperbolic surface of genus 2. Right? It has 2 holes. Right? You can construct this thing by taking, this thing is called, it has a technical name, it's called a pair of pants. Yeah, I didn't invent this name. You can take 2 pairs of pants and glue them. You see there, so this is the 2 legs, and this is where your belly goes, right? And you can take another pair of pants, right? And you can glue together the 2 pant legs in the place where your belly goes, and you get a hyperbolic surface, right? So that's, so you can think of each of these guys as a vertex, and it has 3 neighbors, right? Now, of course, I can take something more complicated and glue them together in a more complicated way, and you will get other hyperbolic surfaces. It turns out that every hyperbolic surface can be constructed like this.
So in an algebraic topology context, we would have a canonical CW complex structure.
Yes, somehow. However, I'm not sure whether that is the right analog or not. I'm not an expert in this area. The point is that I drew here topologically what's going on, but of course you need, the point is, you need a constant curvature metric on this surface in order to write this Laplacian. So this is not what you do, okay? But just if you want to have a picture in your head, maybe this is not so bad. It's not exactly how it's done. The way you do it is and you can do this with graphs too, it just lets natural to think about it combinatorially. You can start with the infinite object, which is a hyperbolic plane. And every hyperbolic surface can be obtained by quotienting this hyperbolic plane by a discrete subgroup of PSL2 of whatever the right group is, right? And you work at that level. So you view the hyperbolic surface as a quotient. And now what you do, if you want to create lips, which I haven't written yet. So what did Maggie and Hyde, okay, let me say what Maggie and Hyde did. They proved that this is true. And how did they prove it? They proved it by making an analog of this construction. So they start with a fixed hyperbolic surface, and then they create random covering spaces in a very analogous way. How do you actually do it? You start with a fixed surface. So this is a quotient of the hyperbolic plane by a fixed group. Does that make sense? And then to create a cover, you duplicate this n times, right? So you take n copies. And then basically you choose an action, you choose a representation of the group onto the symmetric group. You pick a random such representation. And you scramble, right? You mod out n copies of the hyperbolic plane by this randomly scrambled representation of the group on the n copies. And that gives you a random lift. And if you think about it for a little bit, you'll realize that that's exactly what we did here. If we view a deregular graph as a quotient of the, or sorry, if we view a graph as a quotient of the infinite tree, right, then that's exactly the same construction. The difficulty here is that we're no longer talking about the adjacency matrix. We're talking about the Laplacian, and that's a continuous object, right? So the big question in this story is how do you take this continuous object, right, this continuous Laplacian, and encode the spectral information of that in terms of something that's inherently discrete, which is some kind of polynomial of independent or random permutation matrix. And that's much more non-trivial here than it is in the graph case. And you know, that was the kind of major insight of Maggie and Hyde, that one can take this problem about the spectral theory of this Laplacian and encode that into the strong convergence of non-commutative polynomials of permutation matrices. And once you have that, you hit this with the result of Borden-Van Handel. And I can explain how to do this, but not in the time that I have. Okay. So, you see, I mean, this is a problem that seems very complicated, and it is very complicated in a way, but which again, at the end of the day, if you view it in the right way, and that was it was a major insight that can be done, reduces back to, these polynomials of these random permutation matrices are so flexible that you can encode these very complicated problems as a statement about such polynomials, right? But in a non-trivial. Does it make sense? Okay, so in my last 2 minutes, I want to say there have been a lot more developments in this direction. So the applications that I kind of showcased here reduce to the result of Borden-Van Handel. But nowadays we have many new tools to prove strong convergence, and we can prove strong convergence of, let's say, vastly more general models than this one. And I just want to give you a hint. So, one way, what is this random permutation matrix, right? So if I give you an element of the symmetric group, associated to that is some n by n, right? So every element of the symmetric group defines an n by n permutation matrix, which is just a permutation matrix associated to that permutation. Does that make sense? So if I restrict it to the complement of the fixed point, right, I get an n minus 1 dimensional matrix. Is it good? So this map is actually a representation. This is a representation of the symmetric group called the standard representation. This is the standard representation of the symmetric group. And in this language, what Borden-Van Handel has really showed is that if I take an element in the group algebra, right, then the norm of the and I take, let's say, no, I don't want to write it like this. Let's just write it like this. What I say, if I take a polynomial of the standard representation of sigma 1, standard representation of sigma r, it converges to a polynomial of the regular representation of the free group, right? Where sigma 1 to sigma r are independent and uniform from the symmetric group. And now you might ask yourself, well, what happens if I replace the standard representation by any representation of the symmetric group? Let's say non-trivial representation with dimension going to infinity. Right? And do we still have strong convergence? That's not something that follows from the result of Borden-Van Handel. And we can now prove this in kind of remarkable generality, okay? So the standard representation is the representation of dimension n minus 1. And let me just kind of give you the most beautiful, result in this direction to date, which is due to Cassidy, which is that strong convergence still holds for any non-trivial irreducible representation of Sn of dimension less than e to the n to the 1/12 minus delta. Right? For any positive delta. We went from dimension n to dimension e to the n to the 1/12. That's a huge improvement over what was known. And you see, we use the same number of random bits because we're picking a random permutation on n elements, but we're creating vastly higher dimensional random matrices that still converge strongly. So if you're a computer scientist, you call this de-randomization, right? You've created the same effect with much less randomness than you did before. And this is closely connected to very old conjectures in what spectral gaps of representations. There's a huge literature in this area. And for example, if one could prove this for representations of dimension of order n log n, all representations are like this. And one would have proved a long-standing convergent question about whether random elements of the symmetric group, the Cayley graph that they generate has a spectral gap, right? So, we're getting much closer to understanding such questions, and I hope that going further down this road of strong convergence will get us even closer. Good, so let me end there for now.